Hi, I'm Tilman, and I'd like to welcome you and the esteemed audience here in my bedroom to this paper presentation at MobileHCI 2020. This is work that originated from a collaboration between my co-authors Machulla, Niels Henze, and Ken Singer, who was a master's student at the University of Stuttgart at the time. And it's all about cognitive performance. So cognitive performance, such as alertness, fatigue, decision-making abilities, all these things fluctuate throughout the day, partly due to our inner clock. And so in this research, I will show you how we use performance measures obtained from mobile gaming data to model the player's varying alertness levels. And so knowing about the user's systematic performance fluctuations is a prerequisite for what's considered cognition-aware systems. And so cognition-aware systems are technologies that sense, model, and adapt to users' varying cognitive states. So basically these three components: the sensing of the state, the modeling of systematic variations in those fluctuations, and then adapting the user interface or the system behavior accordingly to fit those cognitive states. So that's the goal really here. And from an application layer, we can imagine things such as learning technologies that support memory or that facilitate information processing by adjusting the user interface to the cognitive bandwidth really that the user is available at that point in time. So our physical and cognitive performance is heavily influenced by a complex interplay of biochemical processes. And so Kleitman in 1923 was among the first really to find a link between cognitive performance, chronobiology, and sleep. And so circadian rhythms, or like circadias, meaning approximately once a day, are fluctuations basically of body temperature, heart rate, blood pressure, and so on. These functions in the body. And they influence cognitive functions as well, including alertness and vigilance. They oscillate basically along these diurnal fluctuations and affect our perception, our memory, our decision making, and overall cognitive performance. And so these rhythms are partly behind why at some times during the day we feel rather sluggish and disengaged, and then other times we are ready to take on the world in a sense. And so this is really due to two underlying processes according to established theories on sleep-wake regulation. The one on the left here is the homeostatic process, which manifests itself as a basically gradual decrease in alertness throughout our wake period. So basically, the longer we stay awake, the bigger the sleep drive gets and the more tired we become. And then on the other hand, we have this circadian variations, which basically is a period of 24 hours or a little longer, which follows a sinusoidal pattern and that determines the hours of the day that characterized by particularly low or particular strong sleep. So there are a number of validated tasks to collect data on alertness and cognitive functions. And so in 2017, we published this paper at UbiComp, where we basically bundled some of those into a mobile toolkit for Android to allow researchers to collect ground truth data on alertness and cognitive performance measures. And so the three tasks that were included in that mobile toolkit are the psychomotor vigilance tasks seen here on the left, which is a simple reaction time task. So basically a stimulus, user reacts, we have a reaction time. The second is a bit more complex. It's considered a go, no-go task, and it consists of two stimuli. One, the go stimulus, which calls for an action, which basically is measured in the reaction time, and a no-go stimulus, a stimulus to which the participant has to suppress the urge to react, so basically ignore it. And so on top of that reaction time task, we have this decision-making layer, which resembles a higher cognitive function. And then third, we have the multiple object tracking tasks, which basically is a sustained attention task that requires participants to track multiple objects that move across the screen, and therefore they have to divide their attention across those objects. And so now consumers may not want to perform these tasks for 2 weeks at a time before their devices figure out their alertness fluctuations. And so this should obviously be done in an unobtrusive way. So we use this toolkit, for example, to collect ground truth along with continuously collected data from variable sensors. And so in the case of my colleague Benjamin Tack's work, he's been looking at using EOG data and measuring eye blinks and then correlating that with alertness measures collected through the toolkit. Other colleagues at Cornell, Abdullah and his colleagues basically used a similar task battery to correlate alertness ground truth with phone sensor data and then models to to detect alertness variations. But we were wondering really whether these measures could also be collected through everyday interactions, interaction data such as text typing and also gaming. And games and mobile apps have quite a history in MobileHCI and UbiComp to collect research data in the wild. So who doesn't remember these hits, Hungry Yoshi or Hit It, Tap It, where data was collected through games and that increased basically the external validity through their in situ usage. And so we created this game for Android called Circadian Racer, and it basically gamifies each of those alertness tasks. So on the left, you see a gear changing task, which resembles the PVT. So in order to change gear as quickly as possible, once a message speed up appears, the user has to touch the screen as quickly as possible. The second game mode is an obstacle avoidance task, which resembles the go-no-go condition. So two types of items appear in the driver's lane: obstacles in the form of cars that need to be overtaken, and rewards in the form of oil barrels which need to be collected. And so if the user does not swerve to the other lane in time, the car crashes into the obstacle, effectively launching the third game mode. The car explodes into 4 parts, and the player is required to relocate the positions of their own car's debris after the rubble starts flying across the screen. We also collected a subjective assessment on sleepiness as a ground truth measure using the Karolinska Sleepiness Scale, and we pushed this game then out to about 30 study participants who were reminded to play the sequence of this game multiple times during the day across a 2-week period. And so here's how we analyzed the collected data. Remember, our intention is to see whether there are systematic measure fluctuations in our data that resemble those two processes, the sleep-wake homeostasis and the circadian variations. And so we fitted participants' raw data with those two models. First, the data is examined for a linear performance decrease during participants' waking hours, which is reflective of the homeostatic process. And then second, we examined the data for variability that is not explained by the linear performance decrease, and therefore that may be reflective of time of day dependent influences on performance, which are the circadian fluctuations. And so for this, we compared performance during successive hours. So here are our results. The reaction time increased by 3.5 milliseconds per level of self-related alertness. So we have our validation here. And so we found indications of homeostatic influence in all of those 3 subtasks. And so the orange lines here denote the homeostatic process causing a steady increase in those reaction times, or the committed errors in the case of the multiple object tracking across the day. Our omnibus test also detected significant circadian variations, but pairwise comparisons, ours did actually not yield any significant differences. So here we need to collect a bit more data as the noise between those. So we were able to show our hypothesis that time of day dependent patterns of alertness and cognitive performance can indeed be extracted from game data collected in the wild, as we found indications of the homeostatic process in all of those 3 subtasks. So basically there are systematic persistent changes throughout the day in alertness that we can or that can be detected by a statistical model. It didn't detect any circadian variations. I guess we need more data for that to really show that. And so the reaction time increased by 0.5 milliseconds per hour. And to put that into perspective, in our previous experiments, we had a 1.9 milliseconds increase per hour, but that was under more controlled conditions, really, as you had the tasks that were really close to the originally. So now with the game dynamics on top, we do see more noise in the data, and so therefore also more or less reaction, variations. And so I want to close this with a short discussion about how the game that we presented is tightly coupled with the intended measures, which is a step towards less controlled conditions compared to the previous work. But it does not necessarily imply that any game metrics may be equally effective in changes. And so game designers who would like to incorporate alertness-related features into their gameplay, they will need to look out for metrics that generally represent reaction times, quick decision-making, and visual multitasking. And that's it from our side. You can find the paper with all details in the proceedings of MobileHCI 2020. And if you would like to discuss, feel free to reach out to me or one of my esteemed co-authors. Thanks for watching.